Okay, back again. So now we're looking at graphs, and there's three types of collisions that we're talking about. Just three, and they're actually on your equation sheet. So if you have your equation sheet, you can kind of follow along with the idea. Okay. So here's the equation sheet, and you kind of scroll down your equation sheet, and you get to this section, and you'll see that there's elastic collisions and there's inelastic collisions. And then there's a third one called an explosion equation. And so this might not make too much sense to you looking at this right now, but later on, hopefully the little pictures will make sense. And so, okay. So the first one on the left is an example of a regular old elastic collision. And so I have two carts, and one cart is right here in red. It's kind of sitting there doing nothing at the beginning, and then I give it a push. And so this is me pushing it. So I give it a push with my left hand, going in the right direction. And the blue one is the cart, and it's also sitting there. And then at the same time, I push them toward each other. And so I'm going to push the blue one, which will be a blue mass, right? I'll push a blue mass to the left, right? And that's the velocity. And then the red one, I'm going to take that one, and that has a mass. I'm going to push it to the right, and we are going to add these together. And so what we have here is we have mv b4 plus mv2 b4. So these two objects. And then right here in the middle, I don't know, maybe I'll, should I do black? I'll do black. Right here in the middle, this spot right here, you have this X. And this X is actually where they collide. I don't know, that doesn't show very well. That's where they collide. I'm not sure if green shows up any better. So the collision. And so what ends up happening is the red one, this is a, by the way, this is a VT graph. This is a velocity time graph, a velocity time graph, and a velocity time graph. This is not an XT graph. So anyways, so at this point right here, this is car number one, which is the red car, and it is going to hit, and it was going to go the opposite direction. It's going to bounce, and where's it going positive before? Now it's going to be going negative. So it'll be going at negative speed and go the opposite direction. So this one is now going to be going down the car, down the little way negative. And so this mass, which is the red one, will now be going that way, and the blue one now is bounced off it. They hit right there, bam, and now it's going to go positive, and so the blue one is going to go positive. Okay, so I got a question for you. By looking at these, and this is an MV, and so there's your equation. So by looking at these, I'm going to ask you a question about whether you can tell if one of them is bigger than the other. Okay, so I'm going to actually squeeze this in because I can do that when it's like this, and that will allow me to be able to squeeze this one in right there. So when you look at these, which one of these is heavier, is more massive? And so what we're looking at here is we're looking at delta V, right? Delta V. So which one has the greater change? This is almost exactly like the mom and the daughter, right? Which one has the greater change will be the one that's less massive. And so in the lab, when we do this, which we're not going to do, we're going to have the masses will either be equal to 1 kilogram, and I'm not going to tell you which one it is, right? Actually, I will this time. So the red one is 1 kilogram. Yeah, next one you have to figure it out on your own. And in this one, the blue one is a half a kilogram. And since it's a half a kilogram, actually you can see across the board it's kind of the same. So spoiler alert. So the blue one changed twice as much as the red one because it weighed half as much. So if the daughter weighed or had a mass that was half the mom's, she's going to accelerate twice as much as the mom. And so that brings it right back into Newton's laws. And so that's how you set up these ones. And then, we could do the same thing where we have everything known except for maybe this is the unknown velocity, and we can solve for that. Okay, those are called elastic, and elastic collisions, they bounce. And if it's 100% elastic, then they bounce perfectly. Now that doesn't happen very often in nature, but maybe in the electrical world, that can happen pretty closely in the electrical world when things bounce off each other, in elastic collision. And if it's 100% perfectly elastic, then both momentum and energy and kinetic energy are both conserved. So that's the first one, elastic collision. Okay, second one, in fact, both of these are examples of inelastic collisions. This is the common one we're talking about with cars or with small objects like a ball. So once again, the red object is going to the right because it is the mass is going in a positive direction. This is a positive velocity, and so this little line right there is me giving a push, and I cut off the beginning. Here you can see the beginning, but so here's just me pushing it, and I'm already done pushing, and this is me pushing the blue one. Okay, so that one is going that direction, and I'm going to add it. This is where it collides. So right there, you know what? I'm going to draw it smaller because I don't know, just because I want to see if I can squeeze it in. All right, so this, where'd my pen go? Pencil. Okay, so this mass and this velocity is going that direction. And then this one, same thing, it's going negative, and so that one is going, this mass is going that way. Which one's bigger? All right, the red one's more massive still, spoiler. And this one's twice as small, so it changes more. Whichever one changes more has a less mass. Okay, so that's the beginning. So this is, once again, this is mv, and they're separate. And so when I have them separate, I treat them separate mathematically. Okay. All right. So after, though, equals, look what happens when they collide. All of a sudden, they have the same exact velocity. How is that possible? Well, when they're train cars, you can imagine the two train cars will go, and they actually will go down the track together. Right? So they'll act as one. And so their masses will combine. They don't actually like meld into one object, but if you can picture, that's what trains do when they're separate and they're trying to hook up. They hook and they go down the cart together. And so that's what's happening here is now they're going positive. I can tell because the line is above. And so what color do I have? I have red, right? I have the red mass. And then I have the blue mass, and they're somehow stuck together like Velcro. And there's the blue mass, and they're both going together. I guess I should use purple because they're both going together down the road, right? So that would be purple. You can't really see that, can you? That's purple, right? And so our velocity is purple, right? But they're together. And so our masses are still separate, but I'm going to treat them mathematically as kind of the same, in the same parentheses. So I'm going to add the masses together, and then the velocity will be for both of them. And so that's kind of how that happens. And here is the collision again. The collision is right there. And the law of conservation of energy says that this total will be equal to this total. This is called an inelastic collision. Okay? Inelastic collision. And so in this case, which one's the heavier one? Well, it's the one that actually changes less. Which one's the lighter one? It's the one that changes more. Okay, what are these points? Let's review a little bit. Point 1 is the red car before the collision. Point 4 is the red car after the collision, going backwards at a negative velocity. Point 2 is the blue car before the collision, and point 3 is the blue car after the collision, and now it's going at a positive velocity. Okay, moving on to this one. This is an inelastic collision, and in an inelastic collision, the objects stick together like two railroad cars. They stick together. They don't bounce. In an elastic collision, they bounce. Okay, moving on. This right here, number 3, so 1 is the red car going positive before the collision, 2 is the blue car going negative before the collision, and 3 is both cars going down the track together in a positive direction. And that's another reason we know that the red one is heavier, because the red one kind of won the battle, right? Kind of won the battle of who is heavier. Okay, the last thing we have is something called an explosion, and I think it will make sense when you see an explosion, why it's called an explosion. And what happened to my pen? There we go. Why it's called an explosion. So in this case, instead of doing a ball and two balls, let's actually do like a cannon. Let's do the cannon be red, right? And so the cannon is like this, and the cannon is heavy, right? There's the cannon, right? And on the inside, I'm going to put this cannonball, right? And right now, it's purple because they're together. So the red one is the big cannon, which is twice as heavy. And the blue one is the cannonball, which is lighter. Okay, so what happens here? They explode. This is called an explosion equation. This could happen very easily in class. I have some springs. These carts are actually spring-loaded. And if you touch the spring, you put them together, and you touch the spring, it goes bang, and it explodes them apart. So that's an example of an explosion equation. All right. So in this case, the afterward, this is the afterward, right? Equals. Then you'll actually have the cannon, and the cannon will go backwards. Don't stand behind the cannon, right? Actually, it's very dangerous to stand behind the cannon. It's more dangerous, I guess, in front of the cannon, but you could kill yourself just as well if you're standing in behind the cannon. And the ball is now going to go that way. And so our math on this side will be separate because they are now separated. MV plus MV. Okay, let's think of another example of this explosion equation. So let's take a look at one on the actual quiz. No, not there. Oh, actually, might as well, while we're here, might as well take a look. This is the elastic collision. They are separate before and separate after. I'm not sure if you can see that. They are separate before and they're separate after. And this is the I don't know. I'm messing around too much here. So here we go. So this is separate before, separate after. And this is the inelastic collision where they're separate before, but they're together after. And this one, an example would be a cannon and a cannonball, right? This is the explosion equation. They're before they're together, and then after they're separate. So what am I looking for? I'm looking for right here. Okay, so I'm going to scroll down to this. So check it out. There we go. So this is another example of an explosion equation. Anytime we've talked about this before, you've heard me talk about, oh yeah, America's Funniest Home Videos. It's pretty funny when this person in the canoe, they try to jump to the dock, and the canoe's got no friction whatsoever, and it's a lot lighter than you think. And so you try to jump to the dock, and instead of you going toward the dock, what happens? The canoe goes backwards, and you biff, right? And it's funny. And so we take a video of it, and we laugh at you, and you're all wet. Okay, so anyways, those are our three types of equations that we can use. And in each case, we're simply just looking for one unknown, right? We're setting it up, right, with our mathematical situation. Those are our three, elastic, inelastic, and this is explosion. And then we're simply finding the one unknown. Everything else is known. Okay, so in this one, 3 is the two objects that are together, not moving. And very often in these explosion equations, they're just sitting there not moving. But technically, they could be moving. And then, bam, they explode apart. And once again, you can see the blue one is lighter because it's has a greater acceleration. And the red one is heavier. It has lesser acceleration. And the red one goes to the left because it's negative, and the blue one goes to the right because it's positive. So, man, this is going to be a whole lot of fun, ain't it? So, all right. So if I can find my controls to my video, then I will actually end this video. But I can't. So I guess I'm going to be here a while, and I don't know, we'll just chat about things. What do you guys want to talk about? Oh, there's my controls. Okay. So have a good time in class doing your quiz.